Okay, so we've seen there's kind of a problem here because we have not only one but two paradoxes, and it sounds very weird. Even if we accept, special relativity results that we saw in previous videos, there's still a problem there. Okay, and that problem is, well, the traveler twin can think that, it is actually the Earth twin who is moving away from her and coming back, and therefore it is the Earth twin who should be younger than the traveler twin. It's crazy. There is kind of a paradox here, right? Oh yeah, well, it's due to the acceleration phase, or it's due to, well, the change of frame of reference, blah blah blah, or special relativity just sucks and it's wrong. But actually there's a fourth explanation. It is to actually use special relativity results that we've seen in the previous videos. And then all of a sudden, hey, you get the answer. Interesting, isn't it? Let's see how. Okay, so let's assume that there's distance d between the Earth here and the star we're moving to here. So that's one frame of reference, okay, because we're assuming the star is not moving relative to the Earth. Well, it's a thought experiment, so we do whatever we want, okay? Okay, then instead of two twins, we're going to use triplets this time. And why? Just to avoid the acceleration, deceleration, confusing stuff, okay? So that means we have one twin here, and then we have another triplet here moving from here to there, and at the same time another one moving from in that direction from here to there. Okay, all at constant speed, linear. That way we have three Galilean frames of reference. Therefore we can apply special relativity, and in particular the Lorentz formulas. So that means that okay, the distance, let's say, is 6 light years, and we're moving at 60% of the speed of light. Therefore, it will take 10 years to move from here to there relative to that frame of reference. And the gamma factor, the Lorentz factor, will be equal, according to those values, to 1.25. Good. Then, since we can apply special relativity rules, then we apply the time contraction things, which means that the time here will be shorter by a factor of 1 over gamma. Therefore, the time spent by this guy will be 8 years, as opposed to 10 viewed from here. Okay? Okay. Note that we can get the same result if we use a space contraction and at that speed, instead of time contraction. That's good news. We get the same result. But that solves only the paradox one thing. Now, the paradox two things is using the fact that in relativity, since we're talking about Galilean frames of reference, any frame of reference can be used. And in particular, you can use this one, as opposed to this one. Therefore, you can apply the same, time contraction rule. And since this guy is spending 8 years, in his rocket, or her rocket, then relative to her, this guy will spend 6.4 years, instead of 10. So, there's a problem there. Well, there's a problem because we use only part of the story, of special relativity. Yeah, because if you remember, we used this slide in a previous video where we showed that, in this moving frame of reference, a car moving like this relative to, the ground here where we have two fixed clocks there. And we saw that relative to that frame of reference, this clock was ahead of this one, while from the ground perspective frame of reference, they were synchronized. And the difference between this clock and this clock from this frame of reference was v over c squared times the distance between the clocks. So if we apply that to that particular example, that means that, okay, this guy says, okay, I'm fixed, and this guy is moving, but that means, when I reach this star here, which is in the same frame of reference as this guy, then he will get older by 6.4 years. Okay? So, should I see 6.4 here? No, because actually when I move in that direction, this clock here is ahead of this one by 3.6 years by applying, you know, the v over c squared times distance thing. And that means that, you know, when I arrive here, well, what I see on this clock is 3.6 years plus the 6.4 that I assume this guy has spent while I was gone, and therefore it will show 10 years. Oh, because now that I'm in the same frame of reference as this guy, well, I should see the same thing, you know, on both clocks, which is the case. Interesting. Now that's one direction here. And of course, if we do the same thing in the other direction, well, we get the same type of result, you know. In that case, the clock on the star is lagging behind the clock on Earth here when I'm moving that way, you know. But the result is the same, you know. He's assuming that this guy will only spend 6.4 years. However, the clock here will be ahead of this one by, guess what, 3.6 years, you know, by using the same, you know, factor. Therefore, when I add up the two, I do get the right results. And this guy, when he was actually moving that way, he knew that when this clock was showing 10 years, here, this one was actually showing 13.6, you know? Yeah, from his perspective. And therefore, since he said, well, from this clock, you know, this will last 6.4 years, when I arrive here, it will show 20 years, you know, which is a total of 13.6 plus 6.4. So, what that means is that there is no paradox 2. You know, because as soon as you get together, you know, in the same frame of reference, then everything comes back to the same thing, you know, to the same result. Okay? Which another proof that you definitely should not think in terms of absolute time and absolute, you know, space. It's really important to understand that as soon as you move away from another frame of reference, you get your own time and your own perspective and things change, you know. But what's important is that when you get back to the same frame of reference, well, then you get the same result, which is good news, because otherwise you would truly have a paradox, okay? So that's the mystery of the twins solved, you know, without acceleration, deceleration, changing frames, etc., etc. Okay? Okay. Well, now we are ready to draw some conclusions from that. Okay, well, the first thing is there's not one but two twins paradoxes, okay? There is one twin gets younger to the other one, which is kind of weird, you know. But the other one is because of relativity. Well, you know, in one case you should see one's younger than the other one, and the other case the other way around. Okay, and we showed that it's not true, because you have to apply all the special relativity rules. Not only time contraction, but also time simultaneity, you know, relativity. So that means there were two paradoxes, but in fact there's none, you know. They are not paradoxes, they're just mysteries we had to solve, and we solved them together. Yeah, was fun. Now all you need to do that is just to apply the special relativity formulas, you know. Again, you had to apply you know, the time contraction and the time simultaneity rules. And there's no need for acceleration, you know, to take into consideration the acceleration of a twin, the deceleration when it comes back, all this jazz. I mean, you don't need it. It's useless. Not only it's useless, but it's confusing. Now, in reality, if you look at the original twin story, you know, where the two twins start from the same place and one is moving away, yeah, sure, you will have acceleration then, and also when it gets back, and then when it arrives back with a deceleration. But these effects will be in addition to the special relativity effects that we've seen here, and will be caused by general relativity, which is another topic altogether. So that's great. You know, we explained the to special formulas, special relativity formulas, we explain the whole thing. Again, what you have to remember, and that's key, there's no absolute space, you know, for when you measure distances and you know, the locations of things. Also, there's no absolute time, and that's key, and that's the most difficult part to grasp, okay? But you really have to understand that as soon as you move away from another frame of reference, you get your own, you know, you're on your own, and you can't compare, basically. It's like comparing apples and oranges, you know, you just can't compare. You can only compare times and you know, and distance and things like that in a reliable way when you're in the same frame of reference, okay? So that means at the same time or at the same place doesn't mean anything if you're not in the same frame of reference, okay? So don't try to think, well, while I'm here, what is the time there? No, 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 no. You have to apply the special relativity rules, okay? And otherwise, it's a big mess. Now, at this, you know, day-to-day speed that we use, the difference is so marginal that you can't see it, you can't test it. I mean, it's too small. But when you start to move, you know, near the speed of light, as you saw, then the results can be really dramatic. Okay. And the good news also is we could use simple math, you know, to calculate all of these things using simple, you know, adds, subtract, multiplies, and divides. But again, don't forget, this applies only when you're talking about Galilean frames of reference, okay? Which means only constant linear velocity relative to each other. Okay, as soon as you get accelerations or rotation, which is kind of the same thing, then you cannot apply the special relativity rules anymore. Okay, that's a general relativity thing. Now, if you think you understood everything from these videos the first time you watch them, then probably there's something you did not understand. Okay, I'm sorry, but you know, it's we think we understand. You know, well, everything seems rational, but to really deeply understand the concept, you probably have to run it several times or read other books, etc. Because it's a bit confusing compared to, you know, the centuries for which we have thought in a different way, you know, with an absolute time, which is the same for everyone, you know, which is completely wrong. Anyways, as a bonus, in the next video, we'll see how we can derive the famous equation, you know, E equals m times c squared. Wow, fascinating. So see you in the next video.